found a dead person at work last night, so I don't want that to happen again.
Oh my goodness. Were you wishing for that?
No.
Okay.
They're gonna make
See, it's just been a weird week.
Oh. Okay, well welcome to Gen Chem 2. Something to totally take your mind off of it. So, I gave these out Monday, Alexis. And so here's your copy
Okay, thank you.
of the 7 deadly forces. No, 6 forces of way you connect matter to each other. And so we'll be talking more about that. But actually, if you look a few slides, and I think it's like 16 or 17 slides ahead, you're going to see something that says equilibrium vapor pressure. And you don't have to find it right now, actually, because you're going to see it again. You're going to see it twice. But equilibrium vapor pressure, actually, is in the definition of the boiling point temperature. So we're going to be dealing, when something boils, do you buy this, that it goes from a liquid to a gas? Does that make sense? Okay. So forget about boiling for a minute, and what we're going to do when we talk about equilibrium vapor pressures is I've kind of got in the habit of, let me draw the liquid here. Okay, this is my liquid, okay, and what I think of is I put a watch glass over it, and I know that looks like a sloppy watch glass, but just pretend it's the parafilm or something to seal it up, okay, and then if you've ever watched like a terrarium, what a terrarium does is basically you have soil and you're trying to grow plants, but you seal it up so it has like a little hydrological cycle kind of inside there. Okay, basically you kind of see condensation on the side. But my thing with this watch glass is given amount of time, dependent upon, and we're going to talk about this term volatility, depending upon how volatile that that liquid is, okay, some of that liquid is going to go into its gaseous state. Okay, so I'll put the letter G here. So if you give it enough time, and then here's my other thing I like to do, I somehow take that beaker, which is kind of weird, and I put a pressure gauge. That's my pressure gauge, like one of those dial pressure gauges. It kind of looks like an ear. But that's kind of sensing the pressure of this gas in here, okay? So that's my pressure, gas pressure, indicating what these gas particles are doing. Okay, I'm going to put temperature. I'm going to say temperature is set. That's my last criteria. Basically, I have a certain temperature, and I let this thing go. And some of the liquid particles are going to get enough kinetic energy, and they're going to go into their gaseous state. Some of them, gas particles, are going to lose kinetic energy and go back down to their liquid state. Okay, so that's equilibrium vapor pressure. Equilibrium vapor pressure at a particular temperature. Substances have them. Water has an equilibrium vapor pressure at all different temperatures. Gasoline, like you pump in your car, you could go ahead and set this up, particular temperature, equilibrium vapor pressure. Okay. So we'll be visiting this. You're going to see this diagram a few times. Okay. But in the meantime, let's kind of pick up where we left off with talking about intermolecular, the degree to which matter sticks with itself or other molecules with these intermolecular bonds. So boiling point temperature, I think you guys did in your homework, you guys looked at a few compounds, and these compounds had different boiling point temperatures, and those boiling point temperatures were a reflection on how strong those intermolecular bonds were. So basically, for something to boil, you're right to think of it going from a liquid to a gas. You've got to break these bonds, and so the more intermolecular bonds, then the higher the boiling point temperature needs to be. By definition, we say that a substance has reached its boiling point temperature if its equilibrium vapor pressure that I just showed you a minute ago is equal to the atmosphere. Now, if I go back, and I don't think I can go back, but on your beaker right there, if outside the beaker, I guess one more thing, you would put like 760 millimeters of mercury. That's to say, as we're walking around this room, okay, in terms of pressure in units of millimeters of mercury, it's about 760. 1 atmosphere, 760 torr, right? 1,000 millibars, it's all the same thing. So then when somebody talks, and you're going to see a diagram here to emphasize this, but the normal boiling point temperature is the temperature at which the equilibrium vapor pressure of a substance is 760 millimeters of mercury. Okay, this is almost one of these things where I wish I could go ahead a few slides, but it's kind of circular. So kind of hold that thought. Okay. So again, kind of back to this thing. Okay, back to this thing. We said that the stronger the intermolecular bonds, and this is the strongest and they get weaker, the stronger the intermolecular bonds, the more energy you've got to pump into it in order for it to boil, in order for it to go from its liquid to its gaseous state in a rolling boil. We can have all sorts of situations in which liquid molecules will break their intermolecular bonds to go to form a gas, not at the boiling point temperature. Okay. So in Chem 1, I think we talked about the latent heats, and all latent heats are energies associated with phase changes. So we said in order to get liquid to go to a gas, you have to add energy, and that's the latent heat of vaporization. Okay. So actually I have a diagram here to show you that for a given substance, actually, it's not so surprising that the higher the heat of vaporization, the amount of energy required to make it go from a liquid to a gas, the higher the boiling point temperature. They correspond pretty well. And the higher than the heat of vaporization, then that means that must have more intermolecular bonds that need to be broken in order for it to go to a gas from a liquid. Or did you need that back?
It's all right.
Oh, that's right, I added those little thingies. Okay. So each of these green dots represents a different compound for which we know the boiling point temperature of that compound, and we look up the heat of vaporization for that compound. And so not so surprising when the boiling point temperature goes up, the heat of vaporization goes up, because they're both an indication of, up here with the high boiling point temperature and high heat of vaporization, this would be more/stronger. IM standing for intermolecular bonds. Remember, we're just focused on intermolecular bonds now. We're not talking about chemical bonds. All right. So this is still kind of a continuation of this discussion in the previous part. We talked about these different types of bonds, the dipole-dipole bond, where you have two polar molecules, or pure substance that's a polar molecule bonding to itself. Then we have induced dipole, which basically the darn stuff's not polar, so the only way you're going to get a fighting chance for those two particles to stick together is to momentarily induce a negative region on the molecules. But regardless if it's dipole-dipole or induced dipole or hydrogen bonding, in general, if you get a larger structure, you're going to have more of a fighting chance of getting that last induction of a dipole. So it's more polarizable with increasing molecular weights, kind of like what we talked about last time. So it's more polarizable. You got those kick in more strongly. So with higher molecular weight, you expect it to boil at a higher temperature. So, yeah, isn't that what I just said? For substances similar molecular weight, okay, I guess it's just said a different way. A higher boiling point one will have a greater molecular weight, and a greater molecular weight one will have a higher boiling point temperature. But now be careful, because actually you have an assignment you're going to hand in on Friday that has you rank boiling point temperatures. And make sure you're comparing apples to apples if you're going to go with molecular weight. Because first off, you look for polarity. Okay, actually I went ahead and I wrote down a list of, if you're trying to rank things in order of boiling point temperature, what do you look for first? And it's not molecular weight. Is it polar or not polar? Because if it's polar, dang, you got dipole, which is stronger than induced dipole, induced dipole. Okay, oh, I forgot I had this here. Okay, so molecular weight. The more massive the molecule, the more you can get those dispersion forces going, and the higher the boiling point if that's your goal. But I'm going to show you, we have coming up 3 or 4 compounds that all have the same molecular weight, but the molecular structure is different. Okay, I'm kind of going like this. You're going to see a molecular structure that's kind of spread out or linear, and then you're going to see the same set of atoms that are kind of a ball. Okay, so dispersion forces in a ball don't work very good, because remember, you're trying to get a electron cloud to kind of go one way or the other. Dispersion forces in something that looks like a hot dog, pretty good. You have more surface area here, and something that's linear or spread out, less surface area here. So I wish it weren't so much of an art, but there is this aspect to it. It's not just molecular weight. So there's 2 columns of substances here. You can see that over here on the right, or excuse me, over here on the left, the top says nonpolar. Over here on the right, it's polar. And these are arranged in both cases, nonpolar and polar substance, by increasing molecular weight. So here we have side-by-side boiling point heat of vaporization, boiling point heat of vaporization. So it's kind of nice how they get bigger. Okay, and as they get bigger, your boiling point temperature increases and your heat of vaporization increases for both of them. Before we move on, this is one of the things that kind of I don't struggle with it, but I have to concentrate. There's a difference, I guess. So in Celsius, what's the temperature in this room? About? About what? 15, 20, 15 or 20? Yeah, good ballpark. We'll go ahead and just say 20. So here I'm going to go ahead and insert 20 degrees Celsius, and I'll put an RT for room temperature. All right. And actually, this is kind of one of your homework questions for Friday kind of has you wrestle with this a little bit. But for instance, do you see at the boiling point of first off the bat, what's nitrogen at room temperature? What physical phase is it? It is a gas, exactly. We would have to cool this gas down to negative 196 Celsius in order for it to liquefy. Okay. What's BR2 at room temperature? Boils at 59. Put it this way. It boils at 59, and we're 20. So what do we have to do? Do we have to go up or down to get it to boil? We have to go up. Bromine actually is one of those few liquids at room temperature. So I'm just kind of trying to put that in perspective how that works. So the other thing is these are arranged on purpose. If you go nonpolar, polar, the reason N2 and CO are similar is look at their molecular weights. It just happens to be both 28. It just happens to be. That's how much they weigh in average atomic units, or average atomic mass units, AMUs. Atomic mass units, final answer. But check out the heat of vaporization is similar. The boiling point temperatures are similar. But one is nonpolar and one's polar. And they're paired up. Going across, we have another pair that are, 32, 34 is their molecular weight. We maybe start to see a little more of a difference in their boiling point temperature. Boiling point temperature is something that has stronger intermolecular bonds, okay, is going to boil at a higher temperature. Is negative 88 higher than negative 112? Yeah, again, there's where I have to kind of concentrate. Okay, then we have the next row paired up, and then the following row paired up. With polarity brings stronger intermolecular bonds, higher boiling point temperature. All right. We've seen this before, but let's go ahead. Molecular weight, bringing with it more polarizability, bringing with it the more possibility of those dispersion forces, those induced dipole. Tellurium is your largest, most massive, got the most number of electrons regarding substituting out for the oxygen atom. Okay, so that's kind of, and we looked at this one before. I don't know if over on the side there I had the little molecules, maybe I did. But what this is doing, each line talks about kind of an analogous set of compounds. Okay? But what is so special did we decide about what do H2O, HF, and NH3 have in common? Hydrogen bonding, exactly. These guys, what they all have are H bonding, hydrogen bonding. So it's a step down when you kind of increase mass as you go across with that analogous set of compounds. But you do kind of see a little bit of a trend with regard to boiling point temperatures. An increase of boiling point temperatures with an increase in size. Okay, so we'll be talking more about alkanes. You see where this says alkanes? We're going to talk about, that's a family of compounds that contain only carbon and hydrogen, and alkanes only contain only single bonds too. That's the other cool thing about them. But if we look at kind of a 2-carbon versus a 3-carbon versus a 4-carbon alkane, you know, it's what we've been talking about. The fact that it boils at a higher and higher temperature. Are any of these liquids at 20 degrees Celsius? Nope, all gases. Oh, 5-carbon. 6-carbon. Is that it? Okay. Okay, well, what about pentane and hexane? Are those liquids at 20 degrees Celsius? Yep, they are. Because you can kind of insert 20 degrees Celsius here, add heat, and then you can get this one to boil at 36, get this one to boil at 69. Not to say that some, it won't go ahead and be a little bit volatile, so you'll have it go into its gaseous state a little bit. Okay, so alkanes, I told you, are a family of compounds that contain only carbon and hydrogen. They're hydrocarbons, and all the bonds are single. So the deal is with a bunch of carbon and a bunch of hydrogen, if we look at the values that Pauling said carbon has, Pauling said carbon is 2.5, and Pauling said hydrogen is 2.1. So each bond has a polarity of 0.4, okay? So there's a little bit of tug-of-war going on within these alkanes, but not much. Okay, in general, we say alkanes are nonpolar. Okay, and if they're nonpolar, then if I go back to this, if they're nonpolar, then as far as intermolecular bonds, you're going to have to go with the induced dipole. Yep. Okay. So it's like the trend we've been talking about most recently. What you saw with the 2-carbon alkane up to the 6-carbon alkane was an increase in the temperature at which the substance boils. Now, I'm pretty sure if you go back and look at those 5 alkanes listed a few slides ago, it said that they were N alkanes, so it had the letter N, which means that they were arranged like a hot dog. Okay, there's a difference. Because now I want to kind of briefly go into what happens if you take an alkane, it's only single bonds, carbon and hydrogen, and you ball it up. You have what we call branching. I'll show you what that looks like. Okay, so let's pick on pentane. There's your hot dog pentane. N stands for normal. Okay. There is also a pentane called isopentane. I'm going to show you what that looks like. But basically, we start to get balled up, and I'll show you what that looks like. Still, it's got 5 carbons, 12 hydrogens. Notice that being balled up, being balled up means that it can't have those space it needs to go ahead and have a slightly negative, slightly positive region. It's less polarizable being balled up. And so that means that it's going to boil at a lower temperature. Even more balled up than isopentane is neopentane. I'm going to show you what that looks like here in a minute. Even more balled up, more what we call branching, more balled up, more branching, okay? It boils at even a lower temperature. Okay, so here's the hot dog one. The N means normal, okay? Any compound that ends in the 3 letters ANE, it's a hydrocarbon. ANE means only single bonds, so that's what you see here. Now we start the balling up. So again, this is a type of pentane. This is isopentane, but can you see where it's got one branching spot? So instead of kind of nice having regions where you can have a partially negative and a partially positive, it's a little stubbier. Even stubbier, and this is my favorite, is this neopentane. Isn't that so cool? In each one of these cases of an alkane like this, a carbon has undergone sp3 orbital hybridization. Okay. So are you guys okay? I didn't explicitly say it yet, and we're going to talk about kind of this convention of anytime you see that really means carbon with 3 hydrogens. Okay, and what this really means is it continues with carbon, the carbon chain. Oops, it's got 2 hydrogens. Okay, I hope that works for everybody. It's kind of a shorthand notation. Save the hand cramp. So these are a little way to kind of start to see the kind of the balling up. So if you're trying to do those dispersion forces, you can somehow kind of, the electron cloud can be like partially negative here and partially positive here. It's more polarizable. And if it's more polarizable, then you can have more dispersion forces or stronger dispersion. Okay, here, this bottom one down here, okay, you could get a partially negative, partially positive, but check that out. Okay, it's a spatial thing. It's funny how in chemistry, we aren't going to talk about it too much in inorganic chemistry like this, but in organic chemistry and biology, space counts. Okay, and not to say that you cannot induce a dipole, but not as strong. Okay, so this is weaker. It's balled up, more branching. Okay. So just to kind of summarize, if you're tasked with, and you will be in some way on your test and in homework problems coming up, you're tasked with basically taking an assortment of compounds and putting them in order of what's going to boil at a lower temperature, what's going to boil at a higher temperature. One of the things, after you look at polarity, molecular polarity, polarity of the molecule, then you can go ahead and look at molecular weight, and you can also look at branching. And this is another one of those many things in chemistry where if I'm faced with it, I almost have to doodle it and kind of think through it. You know, so if you find yourself just thinking and mulling it over, that's what I do. So with regard to branching, just like what we saw, you guys caught that the N-pentane, no branching, and the neopentane, the most amount of branching. Branching simply means you're looking for how long, the number of carbons you have in a straight line. So the normal pentane, we had 5 carbons in a straight line. The neopentane, I get 3. Yeah. And you ball it up, and it does not do as well with regard to those dispersion forces. So this is the sort of thing you might be faced with. There's 3 compounds here, okay? Notice that they all are nonpolar. And we could need to put those in order of, look over your shoulder. Cool. In order of what temperature they're going to boil. So let's see. I'm trying to ask this informative question. N-butane. How many people think that that's going to boil at a higher level? Let's see. How many people think it's going to boil at a high temperature? I agree. A higher temperature. Why is it going to boil at a higher temperature?
Because there is more polarity in it.
Well, there's a little bit of polarity within the carbon and the hydrogen bonds, but basically we think of alkanes like this as nonpolar. But it is a higher boiling because there will be more places to have those induced dipole. Okay, so we narrow that down. Propane, you think is going to maybe boil at the lowest temperature? You think this one's going to boil at a lower temperature? Why do you think the isobutane is going to boil at a lower temperature? Well, this one, it seems like it might have, because of the branching, but this one actually has a little more surface area than this one because it has one more blob on it, a nodule. Because so this one has less surface area than that one. So you're saying this would boil at a lower temperature than the normal? Yeah. This one boils at the highest temperature, 0 degrees Celsius, so it's still gas, right? Followed by its branched one. Okay. And then when you get small, when you basically knock off a whole, we call the CH3 groups, we call those methyl groups, when you knock off a whole carbon and its hydrogens of a methyl group and go to the propane, then you have even less intermolecular bonds, especially those dispersion forces. Okay. All right. Well, the good thing here is you guys already did 12-2, right? So let's take a look at the other 2 right quick. Oops. You did this one. I was getting ready to give you hints, and I'm like, wait, we already did that one. Okay. So moving on to this one then. So you need to know a little bit of color here, okay? So the white balls are hydrogen, the black balls are carbon, the red balls are oxygen, and the yellow balls are sulfur. Okay? So what you're supposed to do with number 4 is arrange them in order of increasing boiling point temperatures. Now, you could cheat and look them up if you wanted to, but I would just go ahead, and my hint to you is this, okay? Actually, this checklist As I sit at my office, sometimes I've told students, I'm like, here's your checklist, okay? So finally I wrote it down. Okay, so checklist, if you're dying to make the whole bunch of, to make the strongest intermolecular bond possible, first you look for hydrogen bonding. Okay, and remember with hydrogen bonding, it has to be a hydrogen with an oxygen, hydrogen with a nitrogen, or a hydrogen with a fluorine. Okay, gotta be. So we have a little bit of hydrogen bonding here. The cool thing about hydrogen bonding is that you can then get these strong intermolecular bonds, and you're looking at, in this case, a high boiling point temperature. After that, if it fails or passes or whatever, just generally look to see if the overall polarity of the molecule, is it polar or nonpolar? And these Lewis structures hopefully will help you. But while I'm thinking of it, just to kind of, so we're all on the same page, this D over here, okay, that is an alkane. That's what we've been talking about. Carbon and hydrogen, that's all it's got, black and white, and only single bonds. That is an alkane. In general, alkanes we say are, do we say alkanes are polar or nonpolar? Nonpolar. Yep. So just kind of be aware of that. Look for polarity. Then once you've kind of done that, then you can kind of switch gears to what we were just talking about today. Look, try to compare molecular weight, okay? And if you have identical, those are called isomers, by the way, kind of how we kind of played around with the C5, you know, the pentanes. Those are just, they're called isomers. They're the same atoms. They're just kind of in different arrangements. Then look for branching. Okay, so that's my checklist. So the last one's kind of small. I think I just kind of made it small for some silly reason. But you can see what you're tasked with. You have, let's see, A, B, C, and D. You have 4 compounds. And they're asking you which one would be a liquid at room temperature. And some of them are, in fact, they even say, you know, use your own common sense, because is nitrogen a liquid at room temperature? Yeah. Okay, but I would suggest you jot them down to help justify, because it says explain. Okay, so draw the Lewis structure. The nitrogen's going to be linear, nonpolar, so its intermolecular bonds are just crazy not there. Okay, apply the previous list on the other slide about looking for hydrogen bonding, and then looking for polarity, looking for molecular weight, and looking for branching. And then just kind of consider what the intermolecular bonds would be like overall. Any questions? Okay. Well, we have a little bit of time to go ahead and switch gears is what it feels like. Equilibrium vapor pressure. I'm not going to draw my cheesy beaker again with a little pressure gauge sitting out the side, but hopefully you kind of remember you basically have liquid, you seal it up, okay, and then you let that liquid establish its equilibrium vapor pressure at that temperature. It will. It definitely will. So it's a dynamic sort of thing. Dynamic in that it's, even though that gas particle looks like that gas particle is always going to be there, there's a good chance that that gas particle is going to fall back to become a liquid, and then liquid particle is going to break its intermolecular bonds to become a gas. Okay, so it's like a net wash. It's dynamic. So equilibrium vapor pressure. And like you say, this slide says, if somebody just says VP, okay, that's the same thing oftentimes as equilibrium vapor pressure. Okay. All right, so here kind of is my little beaker over time. So kind of from left to right, you allow time to occur. This is the sealed kind of environment in which that liquid is evaporating. Okay, notice that at first that liquid evaporates into a container that has none of it in there. It's kind of fun. It's like, I'm the first vapor to arrive. Okay, over time, okay, actually we are pushing towards what I call saturation over here. Okay, this would be saturated with that particular vapor. But the middle one, we still have more evaporation than condensation. Of course, evaporation are the red ones, condensation are the blue ones. Does that make sense? Okay. Now here, supposedly, I didn't count them up. See, blue ones, 1, 2, 3, 4, 5, 6, 6 blue ones. Red ones, 1, 2, 3, 4, 5, 6, 6 red ones. Okay. This is where I told you that the gas particle isn't always going to be a gas particle. It might become a liquid, but it's going to be exchanged with something from a liquid becoming a gas. Okay, so the equilibrium vapor, if an equilibrium is established, it's going to stay that way, but it's dynamic. Okay, what looks dead is not dead. So the next slide, I kind of bumped down, so you're going to see it here in a minute. But these series of slides kind of picks that one slide apart. So this is actually a mercury barometer, or setup for a mercury barometer. It's closed. You can't see it very good, but it's kind of closed at the top of the tube. And what this says is basically that liquid mercury has been allowed to fall, and there's that headspace above the liquid mercury. There's nothing. Okay, it's a vacuum. Here's the experiment, or the interesting part of this. We can take a liquid in this syringe, and carefully, this is liquid mercury. But the blue is a different liquid. It's a cool liquid. It's like, oh, I love this liquid. It's a liquid that's probably somewhat volatile. You know something's volatile if you set it out in a pan and you can smell it. One quick test for volatility, okay? So being volatile simply means that actually this liquid here is going to go up into its gaseous state, okay? So to kind of show you what that looks like, I'll pick on purple here. Down here, this liquid, okay, some of it, it's going to go ahead and just like we saw with the little dome a minute ago, basically that liquid is going to establish an equilibrium in that headspace. Notice then what it does that. This gas in here has a pressure. I'll just put pressure of the volatile, no, how can I get pressure of the gas? I don't know. We know there's a pressure, and I could ask you in form of a question, but we know that there's a pressure because check out now how much depressed that mercury's pushed down. Literally, that thing went in there, puffed off some of its liquid to a gas, and jerked that mercury down. How much? By this much. This was the same up there. This is new. This is the pressure of that liquid that's gone to a gas. Pretty cool, pretty cool. Okay. So what this one does, you'd have to kind of look at that previous one and this one side by side, but what this is different is that basically the liquid, the amount of liquid is different. We probably can't tell. Liquid there was smaller, liquid here is larger. All you just need to do is have enough so you have leftover liquid that doesn't all go in its gaseous state. If that's the case, then that equilibrium, that this right here, okay, this is going to be the same regardless of how much liquid. It's like a turkey you inject, right? Regardless of the volume of liquid you put in there, it's going to establish the same equilibrium vapor pressure at that same temperature. Oh, I guess here they are side by side. Same equilibrium vapor pressure of that substance. And here's the cool thing, and this would be fun to kind of run. Basically, if you take something, let's see, what's more volatile? Like, have you ever had like rubbing alcohol and you can like smell it? Like, yeah, okay. So there's that, and what's another one? Something that's stinky. But you could take two stinky things, and actually, depending upon their volatility, they'll establish different equilibrium vapor pressures, and you'll see that depression differ. Isn't that cool? Okay. This one is trying to show you that it doesn't matter the diameter of the inverted test tube, basically, that you use. That does not function. Still same equilibrium vapor pressures established at the same temperature. But this is kind of a neat one. And again, I go back to the stinky thing, okay? People who use those Scentsy candles, you know, they have the warmer things, right? Okay? Without the warmer thing, that smells a little bit. But boy, you go ahead and have that liquid warmed up a little bit, whoo, okay? And that's what's going on, basically. You've established a new equilibrium vapor pressure of that substance at that higher temperature. So here they are, all side by side, lined up. I want to see if we can get a video or two shown right quick. These are good.